All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to be continuing with the prototyping for my autoclipper application. I've been doing a bit more research on various audio related things. Unfortunately, I didn't get a chance to test out how well the model and Hugging Face Transformers pipelines is able to handle a 2.5 hour VOD. I don't think I'm going to be testing that out on stream. I might test it out off stream, but in the meantime, um, there was a bit of research that I felt was necessary to do because this thing came up. This blog post. Well, it didn't come up. It was when I was looking into the chunk underscore length underscore s argument of the pipelines class slash method. I guess it's part of the class, so it's part of the constructor. Either way, it's an argument that has to be passed in either when instantiating the class or when calling it as a method. It's an argument that has to be passed in, and I was trying to understand what exactly this argument does. And to understand this, there's apparently a blog post from back in 2022 that kind of goes into the whole like chunking kind of thing. I was also reading up more on. I guess I didn't really pay attention to this before, but I noticed this bit of detail um, earlier today when I was looking into whisper or distal small en. Let me show it to you guys. I think it's here. Yeah. So under long form transcription, it mentioned that Distill Whisper uses a chunked algorithm to transcribe long form audio files. You know what's interesting? I was assuming that it was pipelines that was handling the whole chunking thing. And so I was like, okay, maybe it's handling like multiple invocations of the model. I still need to look into the actual code for this model and how the thing is being used, which it's kind of interesting. I should try to track it down. Maybe I could like because I'm pretty sure Transformers, Hugging Face Transformers library is open source and it's up on GitHub or maybe some sort of uh, public repo. So maybe I could try asking GitHub Copilot if it can track down exactly where the implementation of Distill Whisper, Distill Small en is, and then it can tell me exactly how the chunking is being handled. So is it like multiple invocations of the model, or is there some other much more efficient way that this is being handled? It also mentioned this in practice, this chunked long form algorithm is 9 times faster than the sequential algorithm proposed by OpenAI, so and so, so and so. Okay. All right. To enable chunking, pass so and so. So this is what got me to, do more research on it. I also looked into batch size, but then when I read up a bit on the documentation, it mentioned that this is well, okay. I haven't fully understood the batching thing, but what I did get from their information in the documentation is that apparently this can increase memory usage, and because they mentioned this thing about issues, out of memory issues, which tells me that adding batching is probably going to increase the memory usage, maybe because it's handling multiple batches of invocations. And another issue that I noticed was that apparently with CPU, like if you're only doing CPU inference, you're not going to see much benefit from batching. And in GPU inference, there are certain situations where you will see benefit from batching and certain situations where you won't see benefit. So what I thought is, later on I can do research on batch size and then I can implement it or use it. I'm not going to be implementing it. Later on I can use it if need be. For the time being, chunk length is much more important to me. So I want to see, okay, what does this mention? Chunk length. This is 15. Distill Whisper uses a chunk algorithm to transcribe long form audio files greater than 30 seconds. So, what I need to see is how well this handles longer than 30 seconds and how much further from 30 seconds can we actually go. Wait, no, hold on. Hold on. I just realized this. Chunk length is 15 seconds, or well, 30 seconds, right? If we don't provide the chunking thing, it's 30 seconds. But will it, like, let's say I don't specify a chunk length. Let's say the chunk length is 30 seconds. Will it automatically do the whole stitching thing? Like, if, let's say I pass in a 10-minute clip, and I haven't specified any sort of chunking stuff, is it still gonna automatically handle the remainder of the thing? I think it should, right? I think it should. Okay, let me also go to just a second. Let me go to BRB so I can open up that page that I want to show you guys. What is this blog post called? Making automatic speech recognition work on large files with Wave to Vec 2 and transformers. So this specific blog post is using Wave to Vec 2, not distilled small en. So I might use Wave to Vec 2 just for the sake of doing this example and understanding what's going on. Okay, making automatic speech. I'm going to type out the entire thing so Google gives me exactly what I'm looking for. Speech recognition work on large files with Wave to Vec 2 in transformers. Okay, here it is. Let's transition back and now we can read this. Right, TLDR, this post explains. Have we transitioned back? Give me a second. Yeah. TLDR, this post explains how to use the specificities of the connectionist temporal classification architecture in order to achieve very good quality automatic speech recognition, even on arbitrarily long files or during live inference. I think live inference is something I should be looking into as well because I feel like live inference is what I would be using with, well, live situations like, continuous audio, actively receiving the audio stream and feeding it into the model. Though in my case, I'm using Hugging Face pipeline. Hugging Face pipe, what? In my case, I'm planning on using Kokoro TTS, but this did get me kind of curious about what it would look like if I just use one of these smaller models. Like, let's say I decided to go with Distill Whisper. No, Distill small en. What if I didn't need to use something like Kokoro TTS? Because, dude, Kokoro TTS is fast. It is great. I have nothing to compare it to. Well, I kind of do. I've compared it to like two or three other models that I tried using, and based on and this was all like after the initial warm up, because there's a warm up because there's a bunch of things that have to be loaded. So you have to give like one, maybe two runs for a warm up, and after that you can judge, you know, how fast the model really is. So I did that with two or three different models, and Kokoro TTS seemed to give me the best results. That being said, this is a straight up. Hold on, I just realized something. Here I'm talking about automatic speech recognition, but Kokoro TTS is not STT, it's TTS. I'm comparing two different things. Yeah, never mind. Let's forget I said anything about Kokoro TTS. Though I was planning on working on I was planning on adding a bit of an STT component to the Stream AI voice app, just so that I'm not, um, just so that I don't have to type as much. Because with the TTS thing, I'm gonna be typing like a lot. I'm gonna be typing a lot. Which, by the way, I'm planning on. Okay, I just realized that why exactly I'm using the TTS thing. I was about to say that, dude, for the past almost month now, I would say I've been actually not well, yeah, for the past month being half of this month and half of the past month, because I was looking at my VODs, and it seems like the last time that I had a slightly long unintentional break was a 10-day period where I didn't stream, and that was like on the I think on the 7th of December. So last year, last month, 7th of December, I streamed, and then the next stream after that was on the 17th of December. So like 10 days just gone like that. No streaming. And it's wild to think that I'm not it's wild to think that I actually did that, and I'm also glad that I'm not doing that anymore. I'm glad that I'm getting into this habit of just constantly streaming. And I was about to say that, hey, now that I am constantly streaming and doing talking streams, do I really still need the Kokoro TTS, the whole Stream AI voice thing? And the answer is yes, I still need it, because I wanted to stream longer. I wanted to be able to stream at different times during the day. And well, one of the things that was holding me back was I'm only able to do talking streams during a very specific window, during a very specific time frame, specific time range. And if I miss that time, then I'm either going to be doing a short stream, or I'm just not going to be doing a stream. So, in order to avoid those kinds of situations, and also in order to extend the period of time that I'm able to stream, I wanted to introduce the Stream AI voice thing. So I can also stream outside of those, outside of that period of time where I'm able to do talking streams. So yeah, I guess it still applies. Hopefully one day I'm going to be able to do more, longer talking streams. But in the meantime, it's going to be a mix of talking streams and AI voice streams. Now, that being said, I think let's continue reading this. Wave to Vec 2 is a popular pre-trained model for speech recognition, released in September 2020 by Meta AI Research. The novel architecture catalyzed. Did I read that right? Yeah. The novel architecture catalyzed progress in self-supervised pre-training for speech recognition. And then there's a bunch of names of something. Maybe these are the researchers. I think so. Yeah, I think these are the researchers. It always confuses me when I read et al. Or et al. I don't know how that's supposed to be pronounced, but like I've seen this in multiple research papers, or at least in the what do you call the section where they are mentioning the names of the researchers in that place where the researchers are being given attribution. There there I see the name of the researcher and then et al. And like that kind of confuses me, and so I saw this and I wasn't sure if I was looking at names. I think these are the names of the researchers, but then it also says the novel architecture catalyzed progress in self-supervised pre-training for speech recognition. Example, it mentions example, and then there's these names. Each of these is leading to a PDF. Oh, maybe they hyperlinked the text containing the researcher's name, but that's linking to a PDF of the research that the researcher did. Right. So generally, like you would be seeing the name of the paper itself, and then that would be uh, converted to a hyperlink that would then lead to the actual paper. But then here they've done it differently. I think so. Okay. Anyways, I'm focusing on this for way too long. On the Hugging Face Hub, Wave to Vec 2's most popular pre-trained checkpoint currently amounts to over 250,000 monthly downloads. Wave to Vec 2 is at its core a Transformers model, and one caveat of Transformers is that it usually has a finite amount of sequence length it can handle, either because it uses position encodings, which is not the case here, or simply because the cost of attention in Transformers is actually whatever that is in sequence underscore length. Meaning that using very large sequence length explodes the complexity slash memory. So you cannot run with finite hardware, even a very large GPU like A100, run wave to vec on an hour-long file. Your program will probably crash. Let's try it. You try it. You try it. Okay, crash out of memory. So this was wave to vec 2. Okay, so then I guess this answers the other question that I was having, which is whether this does the chunking automatically. It doesn't. It doesn't do chunking automatically. My next question was, where does chunk length underscore or chunk length s, where does the chunk length argument go? It doesn't go in the constructor of pipeline. It goes in the method call when you're calling this object as a method. That's where you pass in chunk length. To be fair, I think Gemini might have mentioned this in the code examples, and I just wasn't paying attention at that time to that specific detail. I was paying attention to the other stuff, but not to that specific detail. Okay, so without chunk length, it crashes, and with chunk length, this works and prints a very long string. Now, I believe. Wait, did they link released in September? AI Facebook, okay, okay. They do not have wave to vec. Okay, so here's what I'm gonna do. I'm gonna type out wave to vec in this thing. Actually, I want the exact model. I want this exactly. Okay. Wait. Where am I right now? Okay. Okay. This is what we are looking for. Right. So this, the base model pre-trained. You know what? I have a quick question, which I don't know if I should be asking Gemini or wait, just a second. Yeah. Okay. Okay. Now, here I could ask the question to Gemini directly, right? And then that way, you guys will get to see it on stream as well. I feel like I already have a bunch of these open. What is this conversation for? Oh, I think this is a good place to ask the question. Great question. It's smart to start with smaller, more efficient models. Okay, I think I can ask the question here. Wait, hey, do I need to worry about security when using models? Okay, this question was answered. Okay. All right, so I have another question. I'm looking at Facebook slash what is the name? What is the exact name of this? Wave 2 Vec 2 base 960H on HF model hub. I'm confused about what this model is, what it does, and how I'm meant to be using it. I'm also confused. I kind of want Gemini to explain, first of all, how Wave to Vec works. Actually, I could just look at the architecture. Maybe the paper. Yeah, the paper is mentioned here, right? We can probably open this up and look at the architecture. Though, to be fair, I at this point, at this stage, I might not really understand the architecture. Let's see if we can. Okay, there's no HTML option. Right. Let's open this up. Okay. Yeah, I mean, this is for my own curiosity. I'm not gonna fully understand. I feel like, okay, I think I might understand this if I take the time to read this off stream, because right now I'm just gonna be rushing through the entire thing and I shouldn't be doing that. I also am not entirely sure if I'm gonna fully understand this. I find it interesting that they're using a convolutional neural network here, mostly because I've only ever seen, like so far, it could very well be because I haven't been doing my deep learning research, keeping audio in my, or well, from the audio point of view. A lot of it has involved images. And so that's why it was being mentioned that, oh, CNNs are great for images. Obviously, they're good for other stuff as well. I just haven't been exploring those other things as well, which is why it's interesting for me to see CNN being mentioned here in this very much audio related thing. But yeah, I think I'll look into this after the stream because I definitely want to understand what's going on with this model, and hopefully this model ends up being simple enough for me to understand. You know, being a very much beginner at deep learning and not fully understanding the transformer architecture so far. Hopefully, I'm able to make sense out of this. Okay. Um, Hold on. Yeah. Okay. I will definitely come back to this. For now, okay. I'm also confused about the words. Spelled that wrong. Words in the name. Kindly explain. No write operations necessary. just give me the info. I'm doing this because I don't want Gemini CLI, because Gemini CLI in this specific instance has kind of developed this habit after, probably after seeing, where should I show you guys this? This is one tmux. This is, okay, let's cd into empty directory. Yeah. After seeing all of these Gemini explains markdown files, Gemini automatically just suggests writing to, is this what I was looking at? Oh, okay, yeah, this is what I was looking at. Man, that was fast. Yeah, that was fast. I guess it's because I'm using the light version. What was I saying? Yeah, Gemini, I guess it looks at the files in the directory and it just assumes that, yeah, okay, maybe this person wants the data to be, the response to be written to a file, as opposed to, reading it from the chat itself. Okay, let's go back here and let's also close this because it's going to be eating up a lot of memory. And now let's read this. Let's break down Facebook slash wave to vec2 base 960H. The 960H, from what I've understood, is the number of hours of data that it's been, I believe, fine-tuned on. But that's about all I understand. I don't really understand what that even means, like what exactly the fine-tuning has achieved. But yeah, okay. This is, wait, I also can't remember if it's 960 hours worth of data that it's fine-tuned on or actually trained on. Because at least from what I remember, the base data that it has to be trained on is usually pretty massive. How massive? I don't know. How many hours worth of data that's supposed to be? I don't really know. Okay, anyways. This is a very popular and powerful model for speech processing, particularly automatic speech recognition, or ASR. Here's what each part of the name signifies and how you're meant to use it. Deconstructing the name. Okay, Facebook, this part indicates the original creator and uploader of the model. In this case, it was developed by Facebook AI Research. Oh, that's where fair sec comes from. Sec might be sequence, SEQ, but like on their GitHub repo, I remember seeing this term quite a bit, quite a lot, fair sec, and I couldn't understand where the fair thing was coming from. But okay, that makes sense. Now known as Meta AI, it signifies that this is a model officially released by them. Wave to Vec 2. This is the name of the model architecture. Wave to Vec 2.0, as in Wave to Vec squared, is a self-supervised learning framework for speech representation. What it does, instead of relying on a huge dataset of transcribed audio, Wave to Vec 2 is pre-trained on vast amounts of raw audio, unlabeled speech. During pre-training, it learns to predict masked parts of the audio waveform from the unmasked parts, effectively learning rich and useful representations of speech. Why self-supervised? This approach allows it to leverage massive amounts of easily available unlabeled audio data, making it very effective, even when labeled data for a specific ASR task is scarce. All right. So what I'm gathering here is that this architecture. So they mentioned that it's pre-trained. So I'm guessing it just means training, training prior to us using the model. I could be wrong about that, but it's saying that okay, Wave to Vec 2 is pre-trained on vast amounts of raw audio, unlabeled speech. So this dataset just contains the audio. It doesn't contain any labels mentioning what exactly this audio is. During during pre-training, it learns to predict masked parts of the audio waveform from the unmasked parts. Okay, so what I'm gathering there is that if there are parts missing within this speech, which how are they producing raw audio with with masked parts in them? Like how's that work? I guess I need to read the paper to understand how that's working. Probably the paper is going to give more information on that. Effectively learning rich and useful representations of speech. Okay, great. Base. This term refers to the size of the model. Model architectures often come in different sizes, typically tiny or small, fewer parameters, faster, less computationally intensive, but potentially lower accuracy. Base, a medium sized model, offer, offering a good balance between performance and computational cost. And then large or XL, more parameters, higher accuracy, but um, but slower and more computationally demanding. So wave to vec 2 base indicates a reasonably sized model that performs well without being excessively resource heavy. 960H. This indicates the dataset and duration of the fine tuning for the downstream ASR task. 960H specifically refers to 960 hours of speech data from the LibriSpeech dataset. The original Wave2Vec2 model was pre-trained on much larger datasets like LibriLite and then fine-tuned on smaller labeled datasets like LibriSpeech to adapt it from transcription. So Wave2Vec2 base 960 tells you that this particular base model was fine-tuned on the 960 hours subset of LibriSpeech for its ASR capabilities. What the model is and does. In summary, so-and-so model is a medium-sized, self-supervised, pre-trained speech model developed by Meta AI, which has been fine-tuned on 960 hours of the LibriSpeech dataset to perform automatic speech recognition. Okay, I have follow-up questions. I'll ask it once I'm actually I need a way to copy this. Let's open up a blank NeoVim thing. So my question here is my questions actually. Okay, couple of things. Shit, I'm already forgetting what the questions were. Okay, so you mentioned fine tuning and pre-training. I haven't understood what. Wait, hold on. Um, let's turn on wrap just so it's not, going to the right side. I haven't understood what um, pre-training is exactly. Also, if if we are no if the model is being fine-tuned on 960H of audio data for ASR, then what exactly was it initially trained for? Was the initial trained model meant to do something else? What was the idea there? Okay, what's the next question? 960 hours. Okay, I understood the base part. Was there something up here that I needed to Okay. You also mentioned that, wait, how do I frame my question here? This is, okay, now what is it? What it does, instead of relying on a huge data set of transcribed audio, so it's pre-trained on vast amounts of raw audio, unlabeled speech. During pre-training, it learns to predict masked parts of the audio waveform from the unmasked parts, effectively learning rich and useful. Okay. You mentioned that during pre-training, it learns to predict masked parts of the audio from unmasked parts. I'm kind of confused here. Um, is the model being trained on data that is intentionally missing masked, missing parts? No, this is going to confuse it. That is intentionally masked and or missing parts of it. Like, what's going on there? Then, next question. Let's continue reading here. Uh, this indicates the dataset and duration of fine tuning. Okay, I think I already asked a question about fine tuning. Right. Then, input raw audio waveforms, example, a wave file. Output the transcribed text of the speech in the audio. How to use it? High level. Transformers, pipeline, okay, okay. Let me see if there's a way to do a does can Hugging Face actually compare to models? Like, is that a thing? Because on Hugging Face, the models tend to also have their like some sort of evaluation score. Let me see if I can show it here. I don't know if all of them have it. Okay, there's evaluation results here. To be fair, I am not entirely sure if um, these results can actually be compared. Like results from one thing, I don't know if they necessarily compare one to one with the results of another thing being modeled here. Let me just Google this. What is it? What is it called? Wave to vec to base 960H versus distill small.en. Oh shit, accidentally hit my mic. The primary difference is that Wave2Vec base 960H is a full-sized ASR model focused on high accuracy, while Distill Small is a smaller, faster, distilled model optimized for efficiency on on-device deployment. Oh, so Wave2Vec is going to be heavy. High performance and accuracy on ASR tasks, training model size, inference speed slower than its distilled counterpart. Okay, performance generally achieves better so and so. Typical use research server side applications, scenarios where top accuracy is critical. Okay, yeah, I keep forgetting that I'm not doing this live. As in, I'm not doing live inference. It's gonna be like inference on audio files. So yeah, that's not going to be a problem. Back to this conversation that we were having. Okay, using the pipeline. the easiest way. This abstracts away most of the complexity. You just provide the audio. Wait, hold on. Is there some information here? You can use this model. You use this model primarily for what was mentioned here? Self-supervised so and so, so and so, so and so to perform automatic speech recognition. Okay. You use this model primarily for converting spoken audio into text. The Hugging Face Transformers library makes this very straightforward. Dude, I'm tempted to try and run distill small en. I have no idea how well this is going to work, but I'm tempted to try running distill small en on like an ESP32 if I ever get the chance. But it's not going to be running directly. I think it's going to be. I'm going to have to convert it to Onyx and then either run it through an Onyx runtime or do an Onyx to Burn conversion. And that is assuming that Burn supports, or assuming that the converter supports all of the Onyx operations that are being used in that specific Onyx model. Then I could do the Burnix, no, the Onyx to Burn conversion, and then I'll have a proper neural network that's going to actually run on that can run like directly on the ESP32 hardware. Though there are implementations of the Onyx runtime that have been written for embedded devices. So implementations that are no STD, basically. I need to see how well that would work for me. And yeah, okay. Let's do this first. There's like, dude, there's so many levels here, and I'm so glad that there are entire like ecosystems that kind of help you solve these problems. Because like the fact that I'm able to just the fact that I was able to think about like, okay, in order to run this on an embedded device, I would have to convert this model to Onyx, export it as an Onyx model, and then fortunately we have something like I just realized something. Wave to Vec 2 is a very famous architecture because I've been seeing this mentioned for years. I'm not even kidding about that. I've been seeing this. Well, okay, we can say a good like 2 or 3 years. I've been seeing it mentioned like easily ever since I got into deep learning. I've been seeing this being mentioned. It's one of it's there are many such models that they kind of set the foundation for further research. Where was I going with this? Yeah, my point is I need to check if the candle crate, which is it's a Rust crate made by Hugging Face developers that contains a bunch of implementations for various model architectures that are supported by the Hugging Face Transformers library. I need to see if Wave to Vec is supported in that, because if they've already added support for it, I probably don't need to use Burn then. I could still benefit from using Burn. It's just that there would be a whole like conversion process going on there. But if I go for Candle directly, actually let me check because they do have. Hold on, Rust Candle Wave to Vec 2. Okay, model support, Wave to Vec 2, Hugging Face Candle. Wave to Vec 2.0 is a framework for self-support. This was mentioned in this issue was created in November of 2024. And well, there's no responses to the issue. So I don't know if this ever went anywhere. Let's try opening up Candle itself. The Candle repo, I mean. because they have mentioned support for various things here. Okay, check out our examples: YOLO, Whisper, Llama, T5, Phi 1.5, Phi 2, Segment Anything, Blip, Llama, Falcon, Code, Code Geeks 4, Code Completion, Code Interpreter, Web Search. I didn't know, dude, I need to explore stuff outside of just Gemini. Holy shit, there's so much stuff that I can be exploring, dude. Like, for example, this code completion thing, Code Geeks 4. I didn't even know this was a thing. I haven't been exploring a bunch of other, because I know there's a bunch of like code completion and code understanding and various types of like code related models out there, but I haven't really been exploring many of them. Okay. Right. Sure, I can help you with that. Here's an example of a fast Fourier transform. Implement. Okay. Hell yeah, dude. Great. Okay. I can look into this later on. Then we have stable LM, recurrent Gemma V1 and V2, GLM4, Mamba, Mistral, Star Coder, Quen. Okay. Quantized Llama, quantized Quen, stable diffusion. Um, I'm not sure how to pronounce this. I think it's worst worst chen worst chen maybe. I don't know. That's also it's a text to image generative model. Then YOLO V3 and YOLO V8, object detection and pose segmentation models, segment anything, segformer, whisper, encoder, meta voice. Okay. The list keeps going, and we are at the end. Okay, you know what? I don't entirely know if I'm going to be able to achieve what I'm trying to achieve here. Yeah, I'm not sure if Wave to Vec has actually been implemented here. Though, okay, I'm looking for Wave to Vec specifically. However, Whisper has been implemented. If Whisper has been implemented, then I need to check if distill is any distilled version of it is implemented. But all that being said, I think it would be better for me to go with my older method, which is slightly more complex, but it'll probably give me the results that I'm looking for. That method being exporting the entire model as is to the Onyx format. I'm probably going to have to use, I think it's called Optimum, the Hugging Face Optimum library to export this model to Onyx. And then I'll try to use Onyx to burn to convert the Onyx model into a proper Rust based implementation, Rust based burn implementation of that same model. And then once we have that Rust based burn implementation of the model, we can then easily export this to work on the ESP32, because burn has a no STD backend, which is, what was it called? Something to do with linear algebra. I think it's called N algebra. Or is it N linear? NL algebra? No, hold on. Let me look this up. Rust burn N algebra. Oh, ND array. It's called ND array, not N algebra. Yeah, Burn is both a tensor library and a deep learning framework optimized for numerical computing, model inference, and model training. The term Rust Burn ND array refers to the use of the popular multidimensional array processing crate ND array as a CPU backend for the Burn deep learning framework. The Burn ND array crate provides a pure Rust solution for tensor operations on the CPU. Okay, yeah. So once we have the um, the Rust, the pure Rust implementation of that neural network, then we will be able to use the ND array backend to make it no STD, and through that we'll be able to run it on the ESP32, assuming it doesn't eat up way too many resources and just max out the ESP32. We will hopefully be able to run it. Though in between all this, I also need to look into quantization, as in, what it is, how it works, how we are meant to use it, how we can use it to make a model smaller, quote unquote. Because all I know is that quantization is the process of reducing the precision of the weights, but I don't think it's quite that simple. And I might actually even be wrong about that part. That's how little I know about quantization. But the end result of it ends up being that the model doesn't take up nearly as much memory. And in terms of processing, also, it doesn't take up nearly as much memory and processing power as it would be taking with a much more high precision set of weights. Okay, back to this. So to use it, the easiest way is right. ASR pipeline audio path, dummy audio. Wait, why do we require audio path and then dummy audio as well? Okay, what is SF here? Sound file. Okay. Here we generate 5 seconds of random audio, and then we are writing the dummy audio to audio path. Okay, I thought we are loading something from audio from I thought we are loading something from that audio path. But no, we are writing something to the audio path. Give me a second here. Okay, anyways, transcription. So once we've written the data to the file, then we get the transcription. Output will be a dictionary like so and so. Okay, then we can also use the auto feature extractor and auto model for CTC, more granular control. This gives you more control over over the audio processing and decoding steps. Okay, for now I don't need to look into this. Um, yeah, for the time being, I don't need to look into this. I guess I can ask my questions. Now give me a second because I'm not entirely sure if this is going to copy properly. Actually, I just realized that I didn't take that into account. So I'm going to yank this, but I don't know how well it's going to paste. So just a second. We are just going to switch to BRB. And okay, the paste did not work. Huh. How do I... Oh, you know what I could do? Yeah, I could do that. I could do that. Let's... I'm sure this is gonna work. I'm gonna disable lines, and then we're gonna do Um, we're gonna open up the scroll buffer thing. I forgot what it's called. Um, in Tmux, they have like a, I'm forgetting the name of the thing, but it's like you can enter like a scroll buffer mode kind of thing, and use that to copy the text that is being displayed. Right. Okay. So I pasted it. It looks kind of weird, but I've pasted it. Hopefully it can make out what I'm saying. Yeah, it can strip away whatever is not required. Oh, you know what? It's not that bad actually. It looked broken. Actually, it probably actually is broken. I'm not sure, but yeah. Um, I'm pretty sure the model can handle that. All right, let's read. That's a fantastic follow-up question. As pre-training and fine-tuning are foundational concepts in modern deep learning, especially with models like Wave to Vec 2. Let's clarify both. Let's clarify both points. What is pre-training exactly? You're right to be curious about the what was it initially trained for part. The big idea behind pre-training. Imagine you want to teach something to become a specialized someone. You want to teach someone to become a specialized heart surgeon. You wouldn't immediately start teaching them about heart surgery. First, you need to go through years of general medical school, learn anatomy, physiology, basic diagnoses, basic diagnos. How do you say this? Because diagnosis is one, then you have diagnoses or diagnoses, whatever, basic diagnoses and so on. The general medical knowledge is incredibly broad and fundamental. Once you have that strong foundation, they then specialize. Once they have that strong foundation, they then specialize in heart surgery. In machine learning, pre-training is like the general medical school. Goal of pre-training: to teach a large neural network a broad fundamental understanding of its domain, example language, vision, audio, etc., using a massive amount of easily available data. The goal is not to solve a specific end task like transcribing speech, but to learn rich generalized representations of the data. Data for pre-training. Typically a huge data set that is either unlabeled, like vast quantities of raw text or raw audio, where manually labeling every piece would be impossible or prohibitively expensive, and or self-supervised. The quote-unquote labels are automatically generated from the data itself. The model learns by solving a proxy task like predicting masked parts, as you mentioned. What it learns: during pre-training, the model develops an internal world model or representation of the data. For audio, it learns things like what different phonemes sound like, um, how how sounds connect and form speech, the rhythm and intonation patterns of language, how to distinguish speech from noise, all without ever being told, this sound is for the word cat. Okay, for Wave to Vex specifically, initial training task, self-supervised. The Wave to Vec 2 model was initially trained on hundreds of thousands to millions of hours of unlabeled raw audio. The idea there, um, the core idea was to learn powerful, context-rich representations of speech directly from audio waveforms. Okay, directly from audio waveforms without needing any text transcriptions. This is revolutionary collective because collecting transcribed audio is incredibly expensive and time consuming. By doing this by doing this self-supervised pre-training, the model becomes an expert at understanding the acoustic properties of speech. Was it meant to do something else? Yes, it was initially meant to produce general purpose speech features or embeddings, not to transcribe speech into text. These features capture the essence of what is being said, phonetics, uh, prosody, prosody. I don't know what that means. Um, in a dense numerical form. You know, this is making me realize that um, in terms of like developing these kinds of technologies, because I've been super interested in stuff like speech to text and text to speech and also LLMs. But like this is making me realize that I need to learn a lot of like the base knowledge of how these things work to begin with before learning how to build a model that works with these things, if that makes sense. Because stuff like phonemes and phonetics is like the phonemes thing, and various like NLP related topics, I just don't know them. And so quite often I'll come across various terms and I'm like, okay, what is this? What does that do? And how is that connected here? But if I'm going to be working on these kinds of models, I do need to, and this applies to like anything really. Even when you're working with image data, there's going to be certain extra stuff depending on the type of image data you're working with. Or if you're working with video data, then depending on the type of video data you're working with, there's going to be different um, extra details that you probably should know, which would make it easier for you to um, specialize a model for specific tasks, which is kind of what's been done here. Okay, fine tuning. 960 hours. After this extensive pre training, the model has a deep understanding of speech sounds. Then, to make it perform automatic speech recognition, it undergoes fine tuning. A relatively small task-specific layer, like the connectionist temporal classification or CTC layer, is added on top of the pre-trained model. This combined model is then trained on a much smaller dataset of labeled audio, like the 960 hours of transcribed Libre speech. During fine tuning, the pre trained layers are slightly adjusted, and the new ASR layer learns to map the rich speech representations from the pre trained model to actual phonemes, characters, and ultimately words. So the pre-trained model give so the pre-trained model gave it so the words, holy shit, dude. So the pre-trained model gave it general speech intelligence, and fine-tuning taught it how to apply the intelligence to the specific task of transcribing words. Okay, that's interesting. So the initial training is what's teaching it about speech, teaching it what speech actually is. And then you're able to fine tune it to transcribe speech into words and sentences and whatever. Okay. The masked parts of audio confusion. Your confusion here is common and understandable. It's a key part of self-supervised learning. Is the model being trained on data that is intentionally masked and or missing parts of it? Yes, exactly. This is the deliberate strategy. Like, what's going on there? It's inspired by masked language modeling from models like BERT, but adapted for audio. Here's a simplified breakdown of the process during Wave2Vec2's pre-training. Audio to features. The raw audio waveform is first passed through a convolutional feature extractor. This converts the raw audio samples into a sequence of higher level acoustic features or embeddings over time. Think of it like breaking the audio into tiny overlapping chunks of chunks and representations. Hold on. Overlapping chunks and representing each chunk numerically. Holy shit, dude. Then, random masking. The model then randomly selects contiguous spans, a series of adjacent feature vectors, from this sequence of acoustic features and masks them. Masking means hiding them from the model's view, essentially replacing them with a special mask token, or simply making the model unable to see them. Then the prediction task. Now the pre-training task for the model is to predict the content of these masked spans based on the hold on. This okay, never mind. My thought process was going towards something else. I was like, okay, the masked audio, like within this data set, the masked data, there has to be like a some sort of, here, this is the right answer kind of thing, right? The expected output, essentially. There has to be something like that, I'm assuming, because this is a labeled data set, right? The 960-hour data set is labeled. Okay. Where was I? Now the pre-training task for the model is to predict the content of these masked spans based on the surrounding unmasked acoustic features. However, it's not predicting a specific phoneme or word. Instead it often involves a more subtle self-supervised task. Contrastive loss. The model might be trained to distinguish the true acoustic features of the masked span from a set of randomly sampled distractor acoustic features, uh, other segments from the same audio or different audios. Wait, the model might be trained to distinguish the true acoustic features um, of the masked span from a set of randomly sampled audio words randomly sampled distractor acoustic features. This forces the model to learn highly discriminative representations. Then quantization. In some variations, the model tries to predict a quantized, discretized representation of the masked audio segment from a learned vocabulary of acoustic units. Okay, I'm trying to understand this, but I feel like unless I actually read it a couple more times and properly like test this out myself, I'm not going to fully understand what it means. Um, okay, why this helps contextual understanding. By forcing the model to infer what's missing from the context, it learns to understand the temporal dependencies and acoustic relationships within speech. It learns that certain sounds typically follow others, how different parts of a word or phrase sound together, and so on. Oh, sorry about that. Zoned out. Uh, Robust representation. It creates representations that are rich in phonetic and linguistic information, even without even without any explicit text labels. These representations are then incredibly valuable for downstream tasks like ASR because they provide a powerful foundation of speech understanding. So, in essence, the model plays a game of fill in the blanks with audio segments during pre training. Oh, this is all during pre training. This is not okay. So, my thing about like labels being mentioned there previously, that doesn't apply here, does it? Fill in the blanks with audio segments during pre training, and by becoming good at that game, it develops a sophisticated internal representation of speech. Okay, I'm kind of confused about how the model is able to determine what the right um, answer for fill in the blanks is when the data set is unlabeled. Okay, give me a second here. Okay, here's our response. That's a crucial point of understanding for self-supervised learning, and you've hit on exactly what makes it so powerful. You're absolutely right that the dataset is unlabeled in the sense that there are no human-provided transcriptions like this audio segment means cat during pre-training. However, unlabeled doesn't mean there's no ground truth or no correct answer for the fill-in-the-blanks task. The ground truth for the masked audio segment is derived directly from the original unmasked audio. Oh, so okay, the initial data set is not unmasked. No, sorry, the initial data set is unmasked. It contains audio that is not masked. So the the neural network will read that, and then that becomes what it can be compared against. And during its training process, it's then gonna mask certain parts of this audio or this data. All right. The ground truth of the masked audio segment is derived directly from the original unmasked audio itself. Here's how it works. Imagine you have a long piece of raw audio. The raw audio is the words. The raw audio is the ground truth. Let's say you have an audio clip, sound of the, sound of quick, sound of brown, sound of fox. Okay, the quick brown fox. Creating a training example. During the pre-training process, the system takes, I just realized we were supposed to be doing research on something else, and now we are learning how this wave to vec architecture works and how this training process in general works. I mean, it's still pretty interesting. So like I'm not complaining about that. I'm getting to learn stuff. This is really interesting stuff. So um yeah, I'm not complaining. Anyways, during the pre-training process, the system takes this full audio clip. It then intentionally masks out. Okay, there it is. It then intentionally masks out a portion of it. Let's say it masks sound of brown, then input to the model for prediction. Okay, uh, sound of the, sound of quick, then mask, and sound of fox. Okay, so I'm trying to get an idea of like the bigger picture here. So the idea is that this neural network learns about speech by masking various portions of the audio, and then teaching itself to recognize or predict, in this case, guess what the masked portion is supposed to be. So it has the entire raw audio, and this audio is not labeled. Because there's no labels, so they're using this masking method where they'll remove certain portions of the audio, and see if the neural network is able to predict what the masked portion is supposed to be. And in learning this prediction, the neural network is learning all about speech itself, how various words connect together, what it can expect before a certain word, what it can expect after a certain word, various different ways that words and characters and stuff connect together. It's learning all of these relationships through this process. Okay, the right answer, the ground truth, the right answer that the model is trying to predict for the mask is simply the original sound that that was just masked out. Okay, okay. The self-supervised task and loss. Wave2Vec 2 doesn't try to perfectly reconstruct the raw waveform. This was going to be my next question. What exactly is it predicting? Is it predicting like just features, or is it predicting, well, features or like text embeddings, or is it actually producing the waveform? But turns out that's not what it's doing. Wave2Vec 2 doesn't try to perfectly reconstruct the raw waveform of sound of brown. That's too hard. Instead, it uses a more clever technique, typically a contrastive learning objective. Encoder output. The model first encodes the input data, including the masked parts, into a sequence of contextualized embeddings. The model first encodes the input audio, including the masked parts, into a sequence of contextualized embeddings. Prediction for masked span. For each masked span, the model generates a prediction, another embedding, about what it thinks should be there based on the surrounding context. Contrastive loss. The model is then trained to make a prediction embedding very similar to the true original embedding of sound of brown, which is masked, and very dissimilar to the embeddings of other randomly sampled negative candidate segments from other parts of the audio clip. Okay. The label is internal. The label for this task is essentially comparison. Is the predicted embedding more like the true masked segment, or like these random false segments? The true masked segment is the positive example, and the random ones are negative examples. This positive slash negative labeling is automatically generated by the algorithm itself without human intervention. Analogy. Here, maybe an analogy is going to help. Think of it like learning to recognize objects without anyone telling you their names. You see a full picture of a dog. Someone covers the dog's head. You then try to guess what kind of head it is. Because of the body you can see. Wait, you then try to guess what kind of head it is because of the. Okay, so something has been masked. Okay. You're not trying to name the dog head, but to understand that the covered part is consistent with the rest of the body. All right. The right answer isn't a human label, it's simply the original dog's head that was covered. The task is to learn the visual characteristics of dog heads from the context of dog bodies. So while the dataset is unlabeled for its ultimate ASR purpose, it has an intrinsic self generated label for its pre training task. This is the core magic of self-supervised learning, creating self-supervisory signals directly from the data itself. That is insane, dude. That is insane. Okay, wait, hold on. Okay, couple of questions. Maybe I should write this out somewhere else so I can then copy it here. Okay, couple of questions. What were the questions? I forgot what the questions were. What was my question going to be here? Sorry, zoned out. Okay. I think the first question was so throughout. Wait. Okay. So in this instance, what's the difference between pre-training and training? Or is the pre part just telling us that this model has already been trained and is now going to be fine tuned? Then, next. So, throughout the pre training process, the model is basically learning what speech actually is by intentionally masking parts of the speech so it can later guess what the parts are supposed to be. And in doing so, it is learning all about various aspects of speech itself, like how words connect with uh, each other, how characters connect to form words, and more. I hope this um yeah I, I think this is what I was looking for. Now give me a second, let me just, because I'm not sure if the paste is going to be proper. Okay, the paste is proper. Okay. Wait, holy shit, dude. We have been streaming for close to an hour and a half. Um, and I'm glad that I started the stream early today. Because like I had the chance to do it and I was like, okay, let's not lose this chance. Um, since I'm able to do it today, let's do it today. Hopefully I'm able to go for like another hour. I don't know. Let's see. Um, but yeah, I've been talking for this long. Let me give me a second. Let me take a sip of my energy drink and also hydrate, definitely, and then we can continue reading this. I think after we are done reading this, I should definitely go back to reading about the chunk length thing, because that's kind of what we are looking for. I feel like, dude, there's so many different things that I could specialize in when it comes to deep learning, because I'm much more interested in learning about like deep learning architecture itself, or about deep learning itself, learning about various neural network architectures and how they can be put together in order to solve a certain problem, in order to solve a specific task. I can then pick a certain domain. I can then pick a specific domain, or maybe two or three specific domains that I could specialize in, where neural networks are being used to solve a very specific kind of task, and various neural network related tools are being used to solve a very specific kind of task. And right now, a couple of ones that I'm super interested in, even though I am kind of interested in multiple others as well. But like, yeah, a couple that I am interested in are one, speech to text, text to speech, um, uh, language models in general, large language models in general, robotics, 100% robotics, and there was one more. Oh, yeah, motion tracking technology. Though for the time being, I kind of want to explore the various body pose estimation models out there because I have seen a bunch of body pose estimation models, and I kind of want to try and run them locally and see how well they capture, various details. I also then want to try and apply this to some sort of humanoid model, um, to do like inverse kinematics and just puppeteer animate the humanoid model. Basically, doing something like what's a good example? I don't know what a good example is here because like I keep thinking about live 2D, and like you'd be using VTube Studio for that, but like I'm thinking about 3D. Though, yeah, this applies to live 2D as well. It's just that what gets captured for live 2D then gets translated um, into animatable parameters, or it gets translated into values that can then be used to animate the various parameters of the model itself. Okay, give me a second. Let me you know uh, drink some of my energy drink and also hydrate. Okay, now, um, right. Excellent questions that get right to the heart of how these models learn. Let's clarify pre-training versus training. You've got a good intuition there. Training is the general term for the entire process of feeding data to a model and adjusting its parameters to minimize errors and maximize desired outcomes. Pre-training is a specific phase of training. The pre literally means before the final task-specific training. Oh, task-specific training here is the fine-tuning then, isn't it? Okay, so in the context of Wave to Vec 2 base 960 H, pre-training, the goal is to build a fundamental understanding of speech from vast amounts of unlabeled raw audio. It's like teaching a child the sounds of their native language, how different sounds blend, form syllables, and create natural speech rhythms without ever explicitly telling them the meaning of words or showing them text. Okay. Um, right. Data. Huge data sets of raw audio, millions of hours without any transcriptions, and then output. The model that a model that can extract rich, context aware numerical representations or embeddings from any piece of speech. Um, Wait, a model that can extract rich, context aware numerical representations, which are embeddings, from any piece of speech. These embeddings capture acoustic, phonetic, and even some linguistic information implicitly. Then fine tuning, which is also a type of training, The goal is to adapt the pre-trained, generally intelligent about speech model to a specific downstream task, such as automatic speech recognition. This, okay, back up. The output, now the goal here is to build a foundational understanding of speech from vast amounts of unlabeled raw audio. It's like teaching a child the sounds of their native language. Okay, to build to build a foundational understanding of the speech, to build a foundational understanding of speech from vast amounts of unlabeled raw audio. Okay, all right. So we are teaching them various, we are teaching it, because the example mentioned child. Um, yeah, we are teaching them, in the case of the example, how different sounds blend, form syllables, and create natural speech rhythms without ever explicitly telling them the meaning of words or showing them text. Okay, where was I? Right. So the output is a model that can extract rich, context aware numerical representations or embeddings from any piece of speech. I think what I need to also look into is like a just like a base wave to vec2 model, something that hasn't been fine tuned. Because on their website, they do not on their website, on their GitHub repo, they do have like a list of all of the various models. Facebook's Wave to Vec 2, okay, is there like a GitHub repo? I think in maybe it's not here. Oh, it's here. It's right here. Yeah, let's open this up. Here. Oh, this is, by the way, what I was talking about, fair sec. I didn't know what fair meant there. I also didn't understand what fair sec was, but yeah, I didn't know what fair meant. And well, today I found out. Facebook AI research. Now, here in this list, they mention pre-trained models, and they also mention the fine-tuning part. So you have um, you have Wave to Vec 2.0 base and Wave to Vec 2.0 large, and for each of these, you have different types of fine-tuned versions. So you have one with no fine-tuning, one with 10 minutes, one with 100 hours, and one with 960 hours, which is what we are going to be using. I am curious about the no fine-tuning one and what exactly it produces, because like in this case it mentions that it produces embeddings, right? Once I learn about NLP better through that LLM course, I think all of this will be covered in that LLM course as well. Hold on, do I have that page open? Introduction to audio. I think I can get to the LLM course page from here. Just a second. LLM course. There it is. This is the agent's course. Oh, it skipped away from the audio course. Okay, whatever. So, here, introduction, then natural language processing and large language models. Okay. Transformers models, how do transformers work? Transformers, what can they do? How transformers solve tasks? Transformer architecture. This completely covers transformers for me. That's great. That's amazing, dude. Um, Give me a second. Okay, this course requires a good knowledge of Python. That makes sense. Is better taken after an introductory deep learning course, such as Fast.ai's Practical Deep Learning for Coders, or one of the programs developed by deeplearning.ai. I need to look into both of these, but for now, let me real quick look at what is the thing called? Fast AI's Practical Deep Learning for Coders. Let me take a look at what's being taught there. Fast.ai Practical Deep Learning for Coders. Okay, course.fastai.com. I kind of feel like I've been to this website before, or maybe it's just the layout of the thing that makes me think that. Okay. A free course designed for people with some coding experience who want to learn how to apply deep learning and machine learning to practical problems. Dude, I've yeah, I need to go through this. Yes, I need to go through this. Definitely. Okay, neural net foundations, then NLP, from scratch model, random forests, collaborative filtering, convolutions. So I don't want to go too deep into the training math, if I'm being honest. I kind of want to try and avoid the training math. Though, I mean, there's nothing forcing me to go through the entire thing. So like, I mean, yeah. From scratch model. This is a video. This lesson is based partly on chapter 4 to chapter 9 of the book. The book is on Amazon. Didn't they also mention it's available for free? It's freely available online. Let's open up the book. This is the book. Awesome. Um, MNIST basics, pet breeds, multi-category sizing and TTA, collab, tabular, NLP, mid-level API, NLP deep dive, convolutions, ResNet, arch details, optimizers and callbacks, learner confusion. Conclusion. Huh. Okay. No. Hold on. We so I'm heading into this with some PyTorch knowledge already. I'm glad that I went through that first. Now, where was here? So this does not expect prior PyTorch or TensorFlow knowledge, though some familiarity with either of those will help. After you've completed this course, we recommend checking out Deep Learning AI's natural language processing specialization, which covers a wide. Hold, hold, no, hold on. Um, deeplearning.ai. This is directly leading me to Coursera. Okay, now I need to go to the website. Let's take a look at some of their programs. This dude's face seems familiar. Andrew. I think his name is Andrew. His face is incredibly familiar. Andrew, hold on. Yeah, Andrew, I don't know how to pronounce the next thing, so I'm just gonna say Ing. Andrew Ing. Um, a British American computer scientist and technology entrepreneur focusing on machine learning and artificial intelligence. Now, this person I believe I also follow this person on some sort of social media, but I cannot remember. There's like very specific works of this person. These days, a lot of like their courses are being pushed through through like social media, but I can't remember like their past works. It says here co-founder of Coursera and founder um, of deeplearning.ai. Okay, all right, cool. Explore courses. AI coding, AI frameworks, AI and software, AI safety, anomaly detection, chatbots, compression and quantization, computer vision, data engineering, data processing, deep learning, diffusion models. Okay, so there's like a whole thing here. Um, yeah, okay. Let's not get too distracted with this. So I have some of the very basic deep learning knowledge, and I have basic PyTorch knowledge as well, at least up to feed forward neural networks and building and training um, a feed forward neural network. Okay, great. Who are we? We are so and so and so and so. Okay, awesome, great. These are the people that worked on this course. Amazing. Um, Here are some of the answers to frequently asked questions. Does this course lead to a certification? Currently, we do not have any certification for this course. However, we are working on a certification program for the Hugging Face ecosystem. That's interesting. Okay, that's interesting. I didn't know Hugging Face was working on a certification thing. That can actually be useful for a lot of people. Give me a second. Let me just look this up and see where they're at with this. Okay, it just says here get your certificate, but like in terms of what? Oh, so this one is for Deep RL course documentation. The certification process is completely free. To get a certificate of completion, you need, okay, so this is for Deep RL. So some of these courses do have the certification thing set up already. I don't remember if audio had it or not. I think agents did have it, but they had like a link that you had to go visit. Um, Whereas Deep RL seems to be doing it through Hugging Face Spaces and Google Collab. When we say pass, we mean that your model must be pushed to the hub and get a result equal or above the minimal requirement. All right, cool. That makes sense. Okay, go here, type your Hugging Face username. Oh, I'm curious about this. Give me a second. I'm just going to look this up. Type your Hugging Face username, your first name, last name, and then click on Generate My Certificate. Okay, so this is specifically for Deep RL course certification. Holy shit, dude. Okay, so this is how you do it. Awesome. Awesome. Good to know. And then they have one for the agents thing as well. Um, I wonder if they have one for the LLM course as well. What am I on right now? Oh, we are on the LLM thing. They don't have it for this currently, but they're probably working on it. I mean, cool. Either way, I'm gonna be learning it right now, and then whenever they come up with that certification, then I'll just print that out as well. Where can I ask a question? All right. Okay. Cool. Cool. Awesome. Great. Okay. Oh, they have one for Hindi as well. Maybe I could help out with that. Let me take a look at like what's going on with that and what's the um hold on, this is interesting. They have for Hindi and Gujarati. Oh, they're both being worked on by the same person. Hell yeah, dude. Okay, for some languages, the course YouTube videos have subtitles in the language. You can enable them by so and so. All right, okay, great. I forgot why I was on this page. I completely forgot why I visited this page to begin with. So I'm just gonna move on to this. So we are supposed to be reading up on chunking. Also, let's finish reading this thing. Ooh, that's why I was it was because I was trying to understand or I was trying to see what NLP related topics they're going to be teaching um, during the LLM course. Okay, okay. NLP isn't limited to written text though. It also tackles complex challenges in speech recognition and computer vision, such as generating a transcript of an audio sample or a description of an image. All right, okay. So I don't think this goes specifically into like, speech specific stuff or NLP specific stuff. Maybe it's going to touch on various concepts, but I think they keep the knowledge specific to um, large language models and transformers and how to use transformers to create large language models. Transformer architectures. Let's take a look at this. Encoder models, decoder models. Um, what is this? You can experiment with decoder based LLMs directly in your browser. Okay, it's trying to load something. All right, that's fine. And then there's something here as well. Remember that most transformer models use one of three architectures: encoder only, decoder only, or encoder decoder, sequence to sequence. Understanding these differences will help you choose the right model for your specific task. They also mention how transformers work. We are taking things up a notch. This section is detailed and technical, so don't worry if you don't understand everything right away. We'll come back to these concepts later in the course. Awesome, great. I mean, I'm interested in this. I want to learn how the transformer architecture works. And once I learn about the architecture, then I can just look up some quick information or get Google Gemini to tell me how to train a transformer based neural network. And then I can do that in PyTorch. Awesome. Cool. Um, right. So we're gonna get back to this thing, which I was supposed to be doing, but I am, yeah, I got distracted. Okay, yeah, wait, let's finish reading this fine tuning thing. So, fine tuning, the goal is to adapt the pre trained, generally intelligent about speech model to a specific downstream task, such as automatic speech recognition. So, the initial training taught this model how to understand speech and convert speech into embeddings, so into a numerical representation of some sort. So, we got that part right. Then we have fine tuning, which adapts the pre-trained model to a specific downstream task, which in this case is automatic, automatic, automatic speech recognition. This involves adding a small task-specific layer to the model. Data smaller, what? Oh, the data is smaller, labeled data sets relevant to the words relevant to the specific task. Example, 960 hours of audio with just a second. Yeah. Um, with corresponding text transcripts for ASR. So this is labeled audio. The other audio wasn't labeled. Now I get it. Previously, I'd gotten it wrong, where I thought that the initial audio was labeled, and then the fine-tuned audio is not labeled. Or did I think back then also that the pre-trained the pre-training data set was unlabeled and the fine-tuning data set was labeled? I don't remember. Okay, anyways. 960 hours of so and so. Okay, this is where the model learns to map its internal speech understanding to actual words and characters. Output, a specialized model that can perform the desired task. Example, accurately transcribe speech. So yes, the pre part is telling us that the model has undergone an extensive general training first, has undergone this extensive general training first, and is now ready to be adapted or fine-tuned for a particular purpose. Then, the self-supervised pre-training process for speech. Your understanding is remarkably accurate. Thank you. Hell yeah. So throughout the pre-training process, the model is basically learning what speech actually is by by initially masking parts of the speech so it can later guess what those parts are supposed to be. And in doing so, it's learning all about various aspects of speech itself, like how words connect with each other, how characters connect to form words, and more. This is a great summary. Let's fine tune. I like that. Let's fine tune a couple of points for precision. Learning what speech actually is. Yes, precisely. It's learning the acoustic properties, the phonetic inventory, the distinct sounds that make up speech, the temporal dependencies, how sounds unfold over time, and the prosodic features such as intonation, stress, rhythm that characterize human speech. It develops an internal model of how speech sounds are generated and structured. Then, guess what the parts are supposed to be. This is where the self-supervision comes in. It's not guessing in a human sense, but rather optimizing itself, optimizing its internal representation so that its prediction for the masked segment is as close as possible to the actual original acoustic features of the masked segment. Acoustic features. See, something that I'm now confused about is whether this is like, are we okay? So we are working on audio, we are working on audio data here. I need to keep that in mind because I keep thinking that we are working with like this, the model is converting this data to like numerical representations, but then no, it's the audio data itself that's being worked on. I need to look into like how exactly this is understanding the audio because I think I have a wrong understanding of how that works. Um, so that its prediction for the masked segment is as close as possible to the actual original acoustic features of the masked segment. It compares its prediction to the hidden reality, learning all about various aspects of so and so, so and so, so and so. Yes, but with an important nuance. During pre-training, the model doesn't explicitly know what a word or character is because it never sees text labels. However, by learning to predict masked acoustic segments, again, acoustic segments, so it's audio data that it's predicting. It implicitly learns the acoustic patterns that correspond to word boundaries, subword units such as phonemes or syllables, and the way these units transition from one to another. For example, it learns that the sound k often transitions to the sound however that's meant to be pronounced, like in cat, and that cat is a distinct acoustic pattern. It discerns these patterns from the sheer volume of data without even being told, um, this pattern is C, this is A, this is T, and together they make cat. So it's learning the sound level structure of a language, which then provides an incredibly powerful. Okay, okay, I think I've been understanding this wrong all along. So the model learning is learning about speech, but using audio data, right? For some reason, all this time, I was imagining the model seeing words in pre-training, but in reality, the model is working on audio data directly, isn't it? So any sort of relations that it is learning, any sort of relations and info that it is learning about speech, it is learning by finding patterns and connections in audio data directly. Yeah, see, I feel like I missed that specific part. Like for some reason I was imagining, I don't know what I was imagining, but like I wasn't taking into account that the model might be the model is actually operating on audio data. So whatever it's trying to find, it's looking for it in the audio data. Okay, you've hit on, okay, yes, your revised understanding is absolutely 100% correct. You've hit on the most crucial distinction and the brilliance of models like Wave to Vec 2. For some reason, I was trying to, okay, precisely. During the pre-training phase, Wave to Vec 2 and similar models deal exclusively with raw audio data. There are absolutely no words, characters, or text transcripts involved whatsoever. Think of it this way: text-based models like BERT for language, they learn from vast amounts of text, example, books, articles, etc. They see words, sentences, and paragraphs and learn grammar, semantics, and context by masking out words and predicting them. Audio-based models, they learn from vast amounts of sound, example, recorded conversations, podcasts, speeches, etc. They hear waveforms, frequency, changes in pitch and volume, and learn the intricate acoustic patterns that make up speech by masking out segments of sound and predicting them. Okay, this is why it's called self-supervised learning on so. Okay, now help me understand um, the whole thing about how, man, I don't think we're going to be looking into the chunking thing today. Um, I'm probably going to be reading up on this off stream, but yeah, I'm not entirely sure if we're going to be looking into, because I'm like really interested in this conversation that I'm having right now, because I'm getting to learn so much about this, dude. Okay, now help me understand the whole thing about how the model is learning these relationships. No, how the model is operating on audio data, but producing embeddings as output. And also, like, what kinds of embeddings is it producing exactly? I need to look into that as well, because I haven't had the chance to like properly learn about embeddings. All I know is that embeddings are essentially numerical representations of text, and through those numerical representations, you're able to, like, those numerical representations, they hold semantic meaning for the text. It's not just like a one-to-one like ASCII conversion kind of thing. It's a lot more complicated than that. Um, but like I don't fully understand the concept of embeddings, like how they are created and stuff. So I need to look into that as well. I think I'm going to be learning about embeddings in what do you call it, in the LLM course. Okay, this is a fantastic question because it gets to the core of how deep learning models like Wave2Vec 2 transform raw messy input into meaningful usable information. Let's trace the journey of an input signal through Wave2Vec 2 from raw sound to dense numerical embeddings. Another thing I need to look into is how it's measuring loss. If it's not predicting, oh, maybe it's converting the original audio to embeddings as well. Oh yeah, that was mentioned previously. So it's comparing embeddings. It's comparing embeddings in order to calculate the loss. Um, right. The raw input, a waveform. Imagine you record yourself saying hello. What the computer sees is a raw audio waveform. This is essentially a sequence of numbers representing the amplitude or loudness of the sound wave over time. If your audio is sampled at 16 kilohertz, every second of audio is represented by 16,000 numbers. This is a very low level, high dimensional, and often noisy representation. It's not directly understandable by a transformer. The first step, feature extraction, the ear of the model. Give me a second here. There's just something that I need to take care of. Oh, sorry, zoned out. Where was I? Yeah, the raw waveform first passes through a series of convolutional neural network layers. This part of the model acts like a sophisticated acoustic feature extractor, much like the early layers of a CNN for image detect edges and no. Oh, okay. This part. acts as so and so, much like the earlier layers of a CNN image detect edges and textures. Okay, so just like how the earlier layers of an image, CNN extract um, features like, edges and textures and stuff. So this audio CNN, it acts as a sophisticated acoustic feature extractor. So the idea here is extracting features from it. Purpose: these convolutional layers perform several several critical functions. Downsampling: they reduce the extremely high sampling rate, example 16,000 samples per second, to a more manageable sequence of features, example 50 features per second. This effectively compresses the audio information. That's interesting. I didn't know about that. Local feature learning: they learn to identify fundamental acoustic patterns like different frequencies, onset slash offset of sounds, and other raw phonetic components within small windows of audio. Transformation: they convert the raw amplitude values into a more abstract, higher level sequence of acoustic feature vectors. Give me a second here, just doing something. Okay, the output. The output is a sequence of local acoustic feature vectors. Each each vector um, each vector in this sequence represents a short segment, example 20 to 30 milliseconds of the original audio, capturing its basic sound characteristics. These are a form of embedding, but they are still quite local. They don't yet understand the full context of the sound within the entire utterance. The second step, transformer encoder, the brain of the model. The sequence of local acoustic feature vectors from step 2 is then fed into the transformer encoder. This is the part that makes wave to vec 2 so powerful and is similar to the encoder in BERT. Self-attention's role. The core mechanism here is self-attention. It allows each acoustic feature vector in the sequence to look at and attend to every other acoustic feature vector in the same sequence. It learns the relationships and dependencies between sounds that occur far apart in time, example, how the beginning of a word relates to its end, or how a sound is influenced by preceding and succeeding sounds. Okay, contextualization. Through multiple layers of self-attention and feed-forward neural networks, the transformer encoder takes those initial local acoustic features and contextualizes them. Output: a sequence of contextualized acoustic embeddings. Now each vector in the sequence is no longer just a representation of a tiny slice of sound. It's a rich, high-dimensional numerical vector, example 768 dimensions for wave to vec2 base, that represents that specific sound in the full context of the entire audio utterance. What do these embeddings mean? These contextualized acoustic embeddings are the model's dense. Okay. Um, these contextualized audio embeddings are the model's dense numerical representation of the input speech. They capture an incredible amount of information, phonetic information. Um, they encode what specific phoneme is being uttered, prosodic information or prosodic information. They capture details about intonation, stress, and rhythm. Speaker characteristics. To some extent, they also encode aspects of the speaker's voice through, no, though this is not their primary goal during pre-training, and implicit linguistic information. Crucially, because they were learn through the masked prediction. They will learn through the masked prediction task. They implicitly capture the way sounds combine to form syllables, words, and even phrases, reflecting the underlying structure of language acoustically. They are not direct they're not directly text characters or words. Instead, wait, give me a second. Just doing something here. Okay. They are not directly text characters or words. Instead, they are highly informative numerical summary of the sound packed with context. Why embeddings are the output? Versatility. These rich embeddings are incredibly versatile. Once you have them, you can use them for various downstream tasks by simply adding a small task specific head, um, a few more layers on top. ASR, add a linear layer that maps the embeddings to probabilities over characters or phonemes. Speaker identification, add a classifier that maps the embeddings to speaker IDs. Emotion recognition, add a classifier that maps the embeddings to emotional states. Speech diarization, cluster embeddings to identify different speakers. Transfer learning, by providing these high quality pre-trained embeddings. I'm glad that I did this entire research through Gemini CLI, because now at least it's being shown on stream. Otherwise, it would have all been like in a separate Gemini web UI tab, and none of it would be shown on stream. Give me a second here. Okay, where was I? Transfer learning. By providing high quality pre trained embeddings, Wave2Vec 2 allows other models to start with a very strong understanding of speech, requiring much less labeled data and training time for specific tasks. True, something that is being built on top of Wave2Vec, Wave2Vec 2, is probably going to have access to a ton of extra information. Yeah, dude, that's crazy. So the model operates on audio data by first converting it into a sequence of learned features, then contextualizing those features using a transformer encoder, ultimately producing a sequence of numerical embeddings that are comprehensive, dense, that are a comprehensive, dense representation of the original speech. Okay, I'm wondering how loss is being calculated. Not the math necessarily, but rather how the model knows what the right or close or similar um, answer is. Is it that embeddings are first being generated for the unmasked version so that we have something to compare to at the end? Though, yeah, at the end of an unma at the end of a masked, at the end of a prediction of a masked version. Pretty sure there's a cat walking on the keyboard somewhere. Sure, okay, just insult me. Awesome. Great. Thank you for that. Entangling quantum particles for a faster response. Navigating the slime mold. Gemini's got jokes, dude. Okay. All right, here's the response. I think I scrolled too far back here. Yes, you're precisely on the right track with that line of thinking. That's exactly how self-supervised models like Wave2Vec establish their ground truth for learning without explicit human labels. Here's how it works in more detail. The quote-unquote right answer is derived from the original data's embeddings. You got it. The model creates a target to compare against by essentially generating embeddings for the unmasked version. Let's break down the process. The original audio segment, the true content. You have an original complete audio sequence. A specific segment within the sequence is chosen to be masked for the prediction task. Let's call this the segment origin. Let's call this segment underscore original. Okay, it's a segment that's being. No, hold on. Let's keep reading. Okay. A specific segment within that sequence is chosen to be masked for the prediction task. Let's call this segment underscore original, creating the input for prediction. The model receives the full audio sequence. The model receives the full audio sequence, but with the original, but with segment underscore original replaced by a mask token or simply zeroed out. This is the masked input. The model then processes this masked input through an encoder, convolutional layers plus transformer encoder, to produce its prediction embedding for that mask position, creating the target for comparison, the reference. At the same time, the segment original is also processed. Wait, a specific segment within the sequence is chosen. So we have the entire sequence. The entire sequence is not called segment original. That segment is called segment original, right? At the same time, the segment original, the unmasked true content. Okay, so the unmasked segment is called segment original. The thing hasn't been masked yet. I was wondering, I was kind of confused about that. There's no point in naming the, well, I mean, they could name it for various reasons, right? Anyways, I was confused about that. Okay. Um, at the same time, the segment original, the unmasked true content, is also processed. This is often done by a slightly different version of the encoder, sometimes called a target encoder or a momentum encoder. This target encoder typically uses a smoothed version of the main model's weights or perhaps a copy of the previous training step. This processing of segment original yields a target embedding, which represents the true content of that segment. Okay, calculating the loss, which is the difference. Now the model has two embeddings, the prediction embedding, which is what the model thought was in the mask for context, in the mask from context, and the target embedding, which is actually, no, what actually was in that position processed separately. The loss function, example, a contrastive loss or a form of cosine similarity loss that then works to maximize the similarity between the prediction embedding and the target embedding of segment original. It also works to minimize the similarity between the prediction embedding and target embeddings of other randomly sampled incorrect audio segments. These are called negative samples or distractors. How the model knows what's right. So the model knows what's right or similar, what's the right or similar answer because the original unaltered data itself serves as the implicit label for the masked parts. It's not trying to produce a word, but a numerical representation, an embedding that is acoustically and contextually similar to the true unmasked content. By trying to make its prediction embedding close to the true segment's embedding and far from false segments embeddings, it's forced to learn how speech features relate to each other over time and how to infer missing information from context. Wait, so it's so the embeddings in each case are being generated for segments, not for the entire sequence slash sentence. Okay. That's an excellent clarifying question. It's important to get this distinction right. You are correct. The embeddings are generated for segments of the audio, and the model produces a sequence of these segment level embeddings for the entire input. Wait, I didn't get it. Let's revisualize this process. So raw audio input, the entire audio sequence, okay, thousands of raw samples. Okay, right. Convolutional feature extractor. This first part processes the raw audio performing downsampling and so on, so on, so. No, I feel like I'm a little confused about this. I'm going to need to read this again and maybe refine my question a little bit or ask a couple of follow-up questions. But that being said, guys, holy shit. Holy shit. Damn. Sorry, I was stretching. So, um, I need to reread this and then ask a couple of like follow-up questions. But for the time being, I think I'm gonna drop a raid on someone. Give me a second to go through this section. Hold on. Let's do this. Damn, that's crazy. That is crazy. Holy shit. Just a second, just a second. Hold on just a second. I'm still looking. Still looking. Wait, what's going on here? What is this person doing? Okay. Um, let's keep going. Keep going. Keep going. Um, we're gonna keep going. Okay, okay. Damn, this is going into like much higher. Okay, let's try refreshing again. Okay. All right. All right. Oh, hold on. Is this person okay, foundation. Somebody is doing something with Python, I think. But their stream is follower only, so never mind. Okay, there's someone here who is a new streamer. So I don't know who this person is. I don't know what they do. Um, we're gonna go check out their stream. And yeah, dude. I hope there's no settings on there that prevent me from doing a raid. Yes, no, we're good. Awesome. Right, guys. Holy shit. We made some progress today. I'm so glad that I did this research because I got a chance to learn so much about this, and this is making me even more excited to move forward with that LLM course and also to learn about the transformer architecture and also learn about the convolutional neural network architecture. There's a bunch of stuff that I have to do. For now, I think I need to finish reading this blog post that we were originally supposed to be reading before I got, hella distracted. Um, I'm going to finish reading this because this explains the chunking thing. And then I'm going to see how well this applies to distill small en once I've understood the concept of chunking here. And yeah, then I'm going to finally test out the audio that I have. But yeah, dude, that's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.